So, hello everyone, this is lecture 7 for the nuclear physics. In the last lecture, we have completed the basic properties of nucleus, and today we'll start the radioactivity. So, what is the meaning of radioactivity? See, sometimes nucleus have very excited in a very excited state or have the extra energy, and that's make it unstable, and also its binding energy is, again becomes negative, and that's why it wants to lose that energy. So there are multiple ways by which it can lose. So there is when there is very high amount of extra energy, then it goes to fission, and that fission process not comes under the radioactivity. So in the radioactivity we have alpha decay, beta decay, and gamma decay. So it tries to means there will be little bit less energy as compared to fission, then it will decay alpha decay, and more or less than this, then it will be beta decay, and very small energy extra energy is there, then it will be gamma decay. And beta decay we have beta positive and beta negative decay. So see, when it has a very high amount of extra energy, not that much that it will be fission, but that will be high. So you will have that alpha decay. Alpha decay is nothing but helium ion will be means helium nuclei will be emitted. That will be means now this AXZ will turn out to be A minus 4 and Z minus 2. So this helium nuclei will be out. And now see, there will be a huge amount of mass carried by this helium atom, that is 4 AMU atomic mass unit, and this will give you a very big energy. So this much amount of energy will be released. So that's how it will come to its stable state from the excited states to the alpha decay. And there can be, when there is a little bit less energy, extra less energy, then it will go on to under the beta decay. In beta decay we have that AXZ, then some proton is converted to the neutron, then Z minus 1 will be there, and that proton will go to the it will give you the beta positive decay, and A will remain same, and there will be neutrino particles also emitted. And then when a neutron is converted to the proton, then it will be Z plus 1 here, and this will give you beta negative decay, and it will be anti-neutrino. That's how two beta decay process will occur. And third is the gamma decay. That is nothing but when you have a less energy as compared to means these two, then there will be just like you have in the atom, there is this electron comes from the high energy state to the low energy state and emit a photon. That's how in the nucleus also you will have this gamma decay, and gamma photon will be emitted. So last process will be this. So very much high energy, then alpha decay, then beta decay, then gamma decay. So that's how it will go. And now, as I told you, radioactivity or radioactive decay is the process by which an unstable nuclei loses its energy by emitting alpha, beta, or gamma particles and comes to the stable state. And these characteristic equations for these alpha, beta, and gamma decay are as follows, as I already told you. Now, see, this is the introduction of radioactivity. So, basic thing we need to understand is rate equation, that how this nucleus is decaying into this. So, that comes from the rate equation. So there is this X nuclei and it is turning into the Y. Initially there was N naught X nuclei and they are turning into the Y, and initially Y will be 0. It means one nuclei will convert into the one nuclei in this side. So when it will be N, so at T equal to 0 it will be N naught 0. At particular T it will be N, and here it is nothing but N minus, means N naught minus N will be there. Total sum will always remain N naught plus 0 N naught. N plus N naught minus N will give you N naught again. So they will remain same. Now see, by the observation, this is all the practical results we observe in the actual life. We don't know yet the theory behind this. We are just observing that how it is disintegrating or decaying into the another nuclei. So we have this rate equation, that is dN by dt, means how it is decaying and is decreasing with time. That's why we have this negative sign, and it is proportional to the at that time how much nuclei are present in the parent one. So that is depending on this. So they introduce this relation by taking the observations. Means if you observe that there are 1000 nuclei of particular material, and at particular t time it will reduce to half, 500. Then if there is some other nuclei, that is 5000 particles there, that is again become half, that is 2500 in particular that time. So but see, here half is 500 and here half is 2500. So there will be more nuclear decayed in this time interval as compared to this. So that this thing, that how many they will decay in particular time, that is depending on how much at that time they were present, depending on the n. That's why we have take the dn by dt as proportional to n. So this negative sign can be here also. This is just showing that dn by dt is decreasing with time. So we just to remove this proportionality sign, this will give you dn by dt as minus lambda n. So this integrated is this det will be here, and it is go from 0 to t and n naught to n. At particular time t there will be n, and at t equal to 0 it will be n naught. That's why it is there. Now see, this 1 upon n dn will give you log. So just put the limit, so it will be log n by n naught minus lambda t, dt will give you t. From here, n by n naught is nothing but exponential minus lambda t, and this n is n naught exponential minus lambda t. So this is the equation you use in the 11th standard or the 12th standard. So you are very much familiar with this. Number of nuclei will decay exponentially. You can see here that this nuclei means decreasing or decaying exponentially with time. Now, see, you can just take this lambda in the denominator of this t, 1 upon lambda, and how it will help. So see, whenever you have this kind of equation, then this 1 upon lambda or whatever in the denominator of this is called the scale length. Means in this particular unit time, if it is time, then in this particular time, this thing which is n will decrease to the 1 upon exponential type of time of initial value. That's why it is called the scale length. So we can see that in 1 upon lambda t in time, 1 upon lambda time, this n will decrease to n naught by e, and that is called the mean lifetime. Okay, so that's why this 1 upon lambda is scale length, and it is depending on the 1 upon lambda that how slow will be the process, how fast will be the process. Means if this 1 upon lambda is large, then it will take a large time, and if this 1 upon lambda is small, then it will take the less time. So 1 upon lambda will be less when lambda will be large, and 1 upon lambda will be large when lambda will be small. So that's how you can just relate them. So you just need to understand that this showing the time in which this is value decreased to and not by e. So if it is decreased in large time, then it will be lambda will be small, definitely. This is called the mean lifetime. This is the time in which number of nuclei reduced to n naught by e if initial number of nuclei is n naught. This decay process, fast or slow, it depends on the value scale length 1 over lambda, as I told you, of this exponential decay process. Due to this reason, lambda is called the decay constant, and that's why we call this lambda as decay constant, because this defined the time interval. Now see, we need to find the mean lifetime, that is 1 upon lambda. We'll prove this, how this value comes. In 12th standard or 11th standard, we use direct formula that mean lifetime is 1 upon lambda. And this is that how many time is this whole nuclei will reduce to 0 or 1 upon exponential time. That is called the mean lifetime. And from here you can find the value of lambda also, that is 1 upon tau, that is second is inverse. So if you plot this n with the time, so nt will become half of n naught initial value in the particular time, that is called the half lifetime. So you must remember these terms. So let's find the half lifetime. So we know this equation just from here, n equal to n naught exponential minus lambda t. So n, just write in place of n naught by 2, because it is into half. So that's how we can find the t half. So n naught will cancel out. From here take the log, it will give you this, and t half will be log 2 by lambda, and it is 0.6931 divided by lambda. So this is called the half lifetime. Now see, we need to find the mean lifetime now. So before that, this lambda is the characteristic equation or characteristic of radioactive nuclei. It remains more or less constant. Now this lambda remains constant, means it is depending on temperature, but in general the room temperature, we observe that it is remaining constant for the particular nuclei at room temperature. So now see, x is means we need to find the mean lifetime. So see, first x is turning into the y. So initially it was n naught and it is 0. So it is n naught become n. So it will be nothing but n naught minus n. So this sum will always be n naught. So n plus n naught minus n will give you n naught again. This is also will give you n naught again. So this is at particular time t. So now number of nuclei decayed in time t. So in time t, how many number of nuclei will decay? So that will be n naught minus n. So that decayed nuclei will turn into y. That's why this will remain same as n naught minus n. So now this will be n, and as that will be the number of nuclei decayed in time t. So see, how can you find the mean lifetime? So before understanding that how to find mean lifetime, first you need to understand how to find the average time period of a particular nuclei. So let's say we have these 5 nuclei, okay, and they are decaying at the 10th hour, 11th hour, 12th hour, 13th hour, and 14th hour. So what is the average time of this? So one nuclei at 10, so 1 will by 10, plus 1 at 11, so 1 will by 11, 1 at 12, 1 13, 1 14, and there are 5 nuclei, so that will be this. So this is the average time of this particular nucleus, 5 nuclei. So that's how this is for the particular 5 nuclei, but we don't know how many are there. So we need to find the average lifetime, means for all the nuclei to decay. So how can we find? So let's see, at particular time t, in this dt interval, after this t, in dt interval, there are d and dash nuclei which will decay. So for all the d and dash, this t will remain same, because this is very infinitesimally small. That will be dt time. So we know this t will remain same for all of these. So it will be t into this, t into 1, t into 2, t means all the d and dash. So d and s multiplied t will be there. Means here if time remains same, then you can take the time common, and it will be sum of all the nuclei. So that will be d and s and t. So d and s t, and now you can just integrate this for whole the time. Means to infinity. Means after the time when this decay into the completely, it will completely decay. Then after that there will be no d and s. So this will integration will turn out to be 0. Means this is t d and s. This is similarly as it is written here. Now as we take the time or the d and s as 0 to infinity, means t is taken as 0 to infinity. Now means in particular time when this will decrease to 0, then there will be no d and s, then there will be no meaning of this infinity. So that's why we have taken all the time period. Means in this particular time this will completely decay. So that's why we take this total sum and divide by the total number of particles. So that will be n naught. So that's how you can find the average lifetime. So now we just need to solve this. I hope you get this or not, then you must watch this again. So we need to find this value. So n dash is n naught minus n. We need to find d n dash. So it will be d n dash equal to minus dn. This is constant. This will give you 0. Now from here we know n equal to n naught exponential minus lambda t. So dn will be given as minus lambda n naught exponential minus lambda t dt. So we know dn is minus dn dash. So just substitute in place of dn minus dn dash. This will give you minus minus will become plus here. This will be lambda n naught exponential minus lambda t dt. So now you have dn dash. Substitute dn dash here, and you will get this. Now n naught will cancel out, and you need to integrate this. So we can use the identity here. This is xn exponential minus beta x dx. So this will simply n factorial divided by beta n plus 1. This will be lambda 1 plus 1 factorial. This will be lambda square and lambda. So lambda will cancel out. It will give you 1 upon lambda here. Now see, this is your average lifetime, and this is the same as we discussed here. Now I hope you get it. So we find three things. First was this rate equation n equal to n naught exponential minus lambda t. Second was the half lifetime, that is log 2 by lambda. Third was mean lifetime, that is 1 upon lambda. You must remember all these three things. So let's discuss the successive decay. That is the last topic. So what is successive decay? So normally in the syllabus we will discuss that if A is the nuclear decays to B, if it is still unstable, then it will decay to C, and then we consider that it will be stable. But it is not true. Means it can also disintegrate or decay into D until it will become stable. But in the syllabus which we will discuss, we will consider that up to the C it will become stable. So we will understand what is the rate equation here in the next lecture for this A, B and C, and we will consider them. So we'll discuss in detail about these. So that's all for today. Thank you everyone.